Okay, so in this episode of Current Electricity, I'm going to talk about batteries, how they work. So here are some various batteries. That's a little lithium battery used in watches and things like that. This is a one-time use alkaline battery. Once it's discharged, it's basically gone. That's a rechargeable nickel hydride battery. So this can be recharged and used again. But this big mother of a battery, this is a lead acid battery, the cornerstone of all civilization, or at least the cornerstone of most cars which run on gasoline. So we're going to talk briefly about how the battery works, the electrochemistry behind the scenes. So the story begins by having two lead plates immersed in the acid. So this is sulfuric acid, this blue stuff that you see over here. These are the two lead plates. One of the plates is covered with lead dioxide. Now, lead dioxide is a strong oxidizing agent. So as a result, reduction takes place at this electrode. So the reduction can be viewed as taking place in two steps. So first of all, the lead dioxide, it combines with hydrogen ions in the solution plus 2 electrons drawn from the outside to produce lead oxide and water. So you drop the oxidation state of the lead dioxide. Next, this lead dioxide can be viewed as combining with the sulfuric acid to form lead sulfate and more water. So in all of these processes, the lead is dropping in its oxidation state and you're producing water. So the sulfuric acid is getting consumed. You're forming lead sulfate. So the solution ends up becoming more and more dilute. So that was at the cathode, the positive electrode over here. At the anode, the negative electrode over here, lead combines with the sulfate ions to produce lead sulfate also. But here you have 2 electrons being released. So this terminal here ends up being negative. It becomes a supply of electron for the external circuit. So this is an oxidation reaction that's taking place at this episode, this electrode. So the end result is you have a supply of electrons over here, you have a deficit of electrons over here. This electrode is positive, this is negative. So if you connect an external circuit to it, you have a supply of electrons. And this is basically the battery, how the battery is working. So that was the story about the discharging cycle. The discharging cycle is when the battery is in use. You're using up the lead dioxide, and in this process, electrons are getting sucked in from here. They're being pushed out from there. And so this terminal is the negative terminal, and this one over here, that's the positive terminal. So you have reduction at the plus terminal because you have absorption of electrons, and you have oxidation at the negative terminal because this thing is supplying electrons. Now, once the battery is used up, you use up the lead dioxide, it is discharged. It's dead or on its way to an early death, basically. Then you need to recharge the battery or simply charge the battery. So let's look at that cycle now when you're recharging the battery. So when you recharge a battery that's dead, that's been used up, you connect it to a battery, an external battery or an external source that's more powerful than the battery itself. So you want the voltage coming from the external source or the other battery to be stronger than this. This reverses the direction in which the electrons flow. Because this is more strongly negative than the negative electrode, instead of electrons coming out, they enter over here. On the other side, usually this is the positive terminal. It's a place where electrons get pulled in, but now you have a stronger positive voltage over here. So electron gets pulled out. So the positive and the negative terminals, they reverse their roles as cathode and anode. So now the negative terminal is now a cathode instead of an anode because reduction chemistry takes place there. So let's see how that works out. So we now have oxidation at the positive terminal because electrons are being pulled out. They're being soaked by the charger or the other battery. So the lead dioxide reacts with the water to reform lead, the lead sulfate reacts with the water to reform lead dioxide. In this process, you have H plus ions and SO4 ions being released into the solution. So you rebuild the sulfuric acid which had been used up to form the lead sulfate. And at the negative terminal, over here, electrons are being supplied by the charger. They're being pushed in the reverse direction. So that basically promotes, again, a reduction chemistry at this electrode. So the lead sulfate gets reduced to lead and a sulfate ion. So once again, you have regeneration of sulfuric acid from the lead sulfate. And so the electrodes go back to the previous state. So the positive terminal turns back into lead dioxide, and the negative terminal, the lead sulfate, goes back to just plain lead. So back where it started. So this is the charging and the discharging cycles of a lead acid battery. So and that's basically the chemistry behind how a battery works, such as a lead acid battery. So batteries have two kinds of voltages. One when it's just sitting on the shelf, and one when it's actually in use. So think of a car in a showroom. It's always going to look cleaner and nicer than a car on a street. But what's the use? It's not being in use. So when you use a battery, you find that the voltage drops. So when it's sitting on the shelf not doing anything, that's called the EMF. This is symbolized by script E. And when it's actually in use, you get a lower voltage than what you thought you're supposed to get. So let's look at a quick demonstration of this. So these are two batteries of the same kind. They're both lithium batteries. Now these are two different brands. Look at the open circuit voltage, the EMF, what it puts out when it's not in use versus when you load it up. So the first one here, that's a Duracell. And let's look at the voltage. You see 3.12 volts. Let's write that down. Now let's measure the other battery. These are batteries. I thought I was getting a good, bargain on these things, but turned out the voltage when they're actually in use drops a lot. Let's see. So I'm not going to disclose the brand of this. Let me just call it T, the first letter of the brand. But let's look at the voltage for this one here. 3.28 volts, higher than the other brand, the Duracell. So for battery T, I have 3.28 volts. But that's when you're just measuring it with a voltmeter with no load. Let's now load it. Let's make sure a lot of current is being drawn through from those batteries. And you do that by connecting a resistor across these terminals. So I've now connected in parallel with the meter probes a resistor of 2.2 kilo ohms. So let's now repeat the measurement that we just did before. So this is the battery D, the Duracell. Let's see. It dropped to 3.01 volts. And now let's measure battery T, the other one, 2.83 volts. So this is the point. This particular battery, battery D, it seemed to have a weaker voltage than battery T. When you just measure it with the voltage probes, with a voltmeter that draws almost no current, D is 3.12 volts, and a T is 3.28 volts. However, you draw some current through these things, the voltage drops. This battery D is much more resilient. It drops from 3.12 to 3.01. But battery T, it drops from 3.28 to a lower voltage of 2.83. That's why when I bought these batteries, I measured the voltage and I was thrilled. Like it had like 3.3 volts and I paid almost nothing for the batteries. But when I put them into actual appliances, in many cases, this thing did not work, because when you're drawing a current from it, it drops the voltage a lot. So why does that happen? Let's look at what goes on inside a battery that's dropping the voltage next. So the voltage a battery puts out when it's doing nothing, that's like the car in the showroom, that's called the EMF, also symbolized by script E. EMF stands for electromotive force. And that's the best voltage it can put out when it's basically doing nothing. But the actual voltage that you measure when you're loading it, when you're using current from it, it drops to something called the terminal voltage, a V terminal. This is equal to the EMF minus something lost internally. So every battery, you can think of it as the chemistry that's providing a certain voltage, but there's resistance. When current flows through the battery, there is resistance, and that can be symbolized by this little r. It's the internal resistance. So the voltage that you measure here, if you remember the Kirchhoff's loop rules and stuff like that, you have a positive voltage as you go through the battery, but then you're going through a resistor, even though it's an internal one. So you have a drop in voltage because you're going downstream along the direction of the current. So as a result, what comes out outside the battery, something has been lost in a kind of a tax. So there's an internal drop. And so that can be symbolized by the terminal voltage is E, the script E, minus I times R, just like for an external resistor. And that's the connection between the terminal voltage that actually comes out and the EMF, what the battery was putting out when it was basically doing nothing. And these are the numbers that you had from before. So depending on the internal resistance under actual performance, the battery may do worse. And for the lead acid chemistry we discussed before, as you use the battery, first of all, the EMF, the open voltage it puts out, that drops because the sulfuric acid is getting more and more dilute. So the chemicals are getting weaker. So that's one thing. But on top of that, the resistance, the internal resistance of the battery, it increases. Why? When you reduce the sulfuric acid, you end up with more water. Water is less conductive, so you have more resistance inside. Also, the plates, they're getting covered with this lead sulfate. Lead sulfate is an insulator, so the plates are not making good contact with the electrolyte. Another reason why the resistance goes up. And these are the two reasons why the voltage of a battery drops as you use it. As the battery discharges, both its EMF drops, what voltage it can put out just from the chemistry, and also the internal resistance increases, giving a further drop. And just as a note, in some books, the V term, the terminal voltage, is referred to as TPD, terminal potential difference. Same thing with a different name. Okay, so in this segment, we are going to do an example from the book. We've been using the Jones and Childers textbook. This is problem 18.60. It's a double dot problem. So here they're asking us to find the battery's EMF and the internal resistance. So just as a quick reminder, if you just measure the voltage of a battery like this, so that's the open voltage of the battery when it's not under stress. But as soon as you connect a resistor across it, it's under stress, the current is being drawn. Then when you measure the voltage, you'll get a lower voltage. So I don't have enough hands to do this with this arrangement here, but in the previous episode, I did a demonstration along those lines. So the point of this problem is you connect one resistor, which is a 200 ohm resistor, you have a certain voltage. Then you replace that with a 300 ohm resistor, and you find a different voltage. So based on those voltages, when you have 200 and 300 ohms connected, what is the EMF and what's the internal resistance? So let's get to it. So here I've collected all the information from the problem. The terminal voltage of the battery when you have 200 ohms connected is 9.6 volts. And then the terminal voltage when you have 300 ohms connected is 10.3 volts. What is the EMF and what's the internal resistance? So I've actually added a part to that problem. So this is the equation we saw from a previous episode, that V term is the EMF minus IR. The EMF, that's the voltage the battery puts out when nothing is connected except for this perfect voltmeter. And when you're drawing a current, there's a resistance inside that eats up some of the voltage. Your drop within the battery. Now you're connecting this 300 and 200 ohm resistors externally, so the circuit looks like this. So this whole thing is a battery. This little r is within the case of the battery. These are the terminals of the battery, the plus and the minus, and it's connected to an external resistor, which is R external. This is either 200 ohms or 300 ohms. So these voltages add up according to Kirchhoff's loop rule. So this loop states that the sum of all the voltages around a loop, that's equal to 0. So starting, this is my loop here, the pink thing is clockwise in this case. So starting from this corner over here, going around as you go through the battery, you have the EMF of the battery, and minus the internal drop, minus I times R. Then you have an external drop, minus I times R external. And these three things add to 0 as per the Kirchhoff's loop rule. So next, let's put in some numbers. So you have two sets of numbers for the 200 ohms and the 300 ohm. So for the 200 ohm resistor, you have the same equation. This combination of the script E and IR, that's the terminal voltage of the battery, is the EMF minus the internal drop. So this is V term from the equation which is up here. Okay, so this equation 1 over here. So let's now apply this Kirchhoff's rule, this equation here, for the two cases. Once with the 200 ohm resistor and then with the 300 ohm resistor. So 200 comes first. So here, this equation, the E minus IR, that's equal to the terminal voltage of the battery. And so when you have a 200 ohm connected, at that point you have 9.6 volts for this over here. Some unknown current is being drawn and the R external is 200. So you can now solve this to get I. So with the 200 ohm resistor connected, solve this equation, you get I is 9.6 over 200. So let's label this as equation 3. Now this equation 3, you can put this back into equation 1 up here. So now that you know what I is, and you can then solve for the script E. So let's now put equation 3 back into equation 1. So for the I, we are going to put this 9.6 over 200. That's your equation 3. So, and V term, we know that it's 9.6. So this equation 1 now ends up looking like this. On the left hand side, you have 9.6 volts. That is given to us. That's the terminal voltage of the battery. Script E we don't know. And then for the current I over here, we put the 9.6 over 200 that you have from equation 3. So this gives us equation 4. So you have a single equation with two unknowns, the E of the battery, the EMF, and you have the internal resistance R. So now we repeat this process for the 300 ohm resistance. That'll give us a second equation in this E and R. Then you solve those simultaneously to get E and I, and E and R. And that's the EMF of the battery and the internal resistance. So let's now do it for the 300 ohm resistor. So repeating this process for the 300 ohm resistor, you have the same equation as before. We put in the numbers for the 300 ohm resistor. So with the R external equal to 300, we know that the terminal voltage of the battery is 10.3 volt. These two are given in the question itself. So solve this to get I. So I ends up being 10.3 over 300. So now let's label this as equation 5. You put this equation 5 into the original equation 1, which is over here. So that's the equation 1. So we're going to put this the I value that we just found in equation 5 into equation 1. Equation 1 then looks like this. Okay, so on the left hand side you had the terminal potential difference, the terminal voltage. So that's 10.3 given in the problem, the question itself. E we are trying to solve for. You had I times this little r. I came from equation 5. So put the 10.3 over 300 over here. Now this equation can be simplified and solved for E. So this E over here, rearranging this, gives us the following equation, which we'll call equation 7. So from equation 7, you have one solution for E. We are going to solve this simultaneously with the previous equation 4. So insert 7 back into equation 4. Equation 4 was this equation over here. Okay, so here is the equation 4. And we're going to put this equation 7, put equation 7 into equation 4. So upon doing that, we end up with this equation over here. So we had equation 4, 9.6 is equal to E. Instead of this E, put this whole thing over here. So that's 10.3 R over 300. And then in equation 4, you already had minus 9.6 over 200 times little r. So now notice in this whole equation, the only thing that's unknown is this little r over here. So first of all, solve these fractions, which are 0.034 and 0.048. And now solve this equation for R. Is the only unknown. So R ends up being 10.3 minus 9.6 over this 0.048 minus 0.034. So when you solve this, you get the internal resistance of the battery. So within the battery, you have 51 ohms already in there. Now that we have solved for little r, you can put this back into equation 7. So if you put the value of r over here, you can solve and get this E. So doing that, equation 7 now becomes all of this, replaces r with this 51 ohms over here, crunch this out, and that gives you 12.05 volts for the EMF. So this is the what's called the open circuit voltage of the battery. If you just put an ohm meter with no other resistors, nothing else going on, that's the battery's voltage when it's not under stress. And the reason it gets stressed when you're drawing current is because there's an internal resistance within, which eats up the voltage and drops the voltage. And that internal resistance for this battery is 51 ohms.